So very good morning all the students. Today, before starting the next unit, that is unit number 2, we will see the basic IS code which is required for your IS, which is required for earthquake resistant design. This is 1893-2002, because on the basis of this IS code we will analyze the various buildings and also the various theoretical aspect as well as the design approach are available in the same code. So let us start with the IS 1893-2002 general provision of the buildings, part 1. So first of all, if you see, we can't stop the earthquake from occurring. That is, it is a natural phenomenon, but we can come up with the effective way of reducing the risk and mitigating the damage. This is the basic aim and the aspect and the background of the study of this particular subject. So why earthquake resistant designs? First of all, we see why this earthquake resistant design is required. So if you see this graph, so there are 5 or 4 natural calamities. If you see that, out of that, earthquake is very predominant, okay, as compared to flood, hurricanes and volcanoes. Okay, so the chances of earthquake as a natural calamity is much higher than the other calamities. Okay, so if you see, or if you plot the fundamental time period versus acceleration, if you plot the graph, then you can see that this is a earthquake prominent zone and second is a wind prominent zone. Okay, so based on that, if you see that the earthquake prominent zone, it start with a very high acceleration, then it goes on reducing to a certain level. But if you see the wind prominent zone, it will start with a very low acceleration, then at the center it will rise and then suddenly drop down. Okay, but with the comparison of the wind, the earthquake is somewhat more predominant and very effective as compared to the wind zone. So this is the outline of the revision of IS 1893. Okay, so in this case we will going to see the structure of IS 1893 after 5th revision. Although there is no a new revision is of the code is come, that is IS 1893 2016, but that is the basic changes which are come in the same revision. That is the structure of IS 1893 after first revision, then seismic zone map, then design lateral forces, seismic coefficient method is there, response spectrum method is there, load combination, that is multi-component is there, and torsion is there. So one last topic which is left in our unit number 1, that is response spectrum, we will cover in this part of 1893. Okay, so next is outline, deformation, design, interstory, separation between the adjacent unit, compatibility requirement, then configuration and foundation. So first of all, we will see the various IS 1893, that is the various earthquake codes which are applicable for the different types of civil engineering special structures. So first is general provision and the building, that is part 1, which is applicable to our syllabus. Second is liquid retaining tanks, elevated and ground supported structure, that is part 2 is there, IS 1893. Then third is applicable for the bridges and retaining wall. Then fourth is applicable to the industrial structures like stack, etc. And part 5 is applicable for dams and embankment. So in future, if you are looking for the design or earthquake design of some special structure, so you refer these codes. So first of all, we will see what are the measures and important changes which will take place in this code. So the revision of the seismic zone map 225. 225 means in the first edition of IS 1893, that is far in 1983, the zone was divided into total 5 zones, zone 1, 2, 3, 4, 5. But in this IS 1893 2002, zone 1 and 2 are merged. Therefore, the zone will be recalled as zone number 225 after the merging in 1893 2002. And next is the value of the seismic zone factor are changed, reflecting effective peak ground acceleration MCE, that is moderate considerable earthquake, and service life of the structure. Then response spectrum for the 3 types of strata is considered, that is hard soil, medium soil and soft soil. Then empirical expression for estimating the fundamental natural time period of multi-story building is considered. So the intensity zone is bifurcated as shown on the screen. Then the introduction of response reduction factor is there due to the ductile deformation. Then lower bound design based shear is considered. Soil structure interaction is there, torsional eccentricity is there, model combination is there. These are the major important changes which are takes place. We will see step by step when we will go through the details in IS 1893. This is just changes and outline. Okay. Then the terminology for the earthquake engineering. So it is the important part. This all terminology which is shown on your screen, these all are available in the IS 1893 2002 in page number I think 325, in between 3 to 5. So you just go through that IS 1893 2002 because these definitions are very much important as far as the numerical is concerned. So first of all, closely spaced mode, that is the definition is there. Closely spaced mode is of a structure is nothing but it's a natural mode of vibration, and which is having the natural frequency which is differ each other by means of 10%. Okay. Then critical damping is there, the damping beyond which the free vibration of motion will not be oscillatory. Then damping, the effect of internal friction which is imperfect elasticity of materials, slipping and slide, and in reducing the amplitude of the vibration and express the percentage of the critical damping. Then design acceleration spectrum, it is nothing but an average smooth plot of the maximum acceleration as a function of frequency or the time period, and for the specific damping ratio for the earthquake excitation at the base of the single degree of vibration. Then the design base earthquake DBE, which is called it is nothing but it can be reasonably be expected to occur at least once during the design life of the structure. So next is design horizontal acceleration coefficient, AH is there. The design lateral force is there. Okay, ductility is there, definition. Then epicenter is there, effect of peak acceleration is there. Then flow response factor is there. All these definitions, all these parts are available in IS 1893 2002. So you just go through that. Okay, and then next is focus originating earthquake sources of the elastic waves inside the earth which causes the shaking of the ground due to earthquake. Then importance factor is there, this factor which is used to obtain the design seismic forces. Okay, and which is characterized by the hazardous consequence of its failure, and the post earthquake function needs the historic value and or the economic value. Then intensity of earthquake is there, liquefaction is there, magnitude of earthquake is there. Okay, so all these terminologies are also applicable in your unit number 1. Okay, so you just refer this as per the reference of IS 1893. So next is maximum considerable earthquake MCE, then modal mass is there, then mode shape is there, then natural time period is there, that is a structure having its time period of undamped free vibration, then fundamental natural period is there, then modal natural period is there, okay, then response reduction factor is there, response spectrum. This is the part which we left in unit number 1. So based on the definition you can write the theory. So response spectrum is nothing but a representation of a maximum response idealized single degree of freedom system. SDOF means single degree of freedom system having the certain time period and damping, and during the earthquake ground motion, and the maximum response is plotted against the undamped natural period versus for the various damping value, and can be expressed in terms of maximum absolute acceleration. Or you can simply define this terminology as a plot between the natural time period versus the absolute acceleration, which is plotted on y-axis. So if you plot the graph between natural time period as on x-axis, whereas the absolute acceleration on y-axis, so based on that, whatever the peak acceleration you will get during an earthquake, that is being recorded as an response spectrum. Then seismic mass is there, then seismic weight is there, then structural response factor is there. Okay, these all the terminology are very much applicable in your calculations. Okay, so you just go through that. Next is time history analysis. So time history analysis is nothing but a dynamic analysis. Look, basically for analyzing the building by using earthquake method, there are two basic methods are available. First is your approximate method is there, that is also called as a seismic coefficient method, and second is a dynamic method. So the time history method, response spectrum method are the part of the dynamic analysis. Okay, then second is a zone factor. It is a factor which is obtained the design spectrum which depend upon the perceived maximum seismic risk characterized by the maximum considerable earthquake in the zone in which the structure is located. Then zero period acceleration is there, then center of mass, center of stiffness, design base shear, diaphragm, dual system is there. Okay, these all are directly and indirectly related to your numerical part. Okay, and some of the theoretical part or some of the theory or the definition may be asked in your examinations. Okay, so based on the question paper you can refer this. Okay, then height of the floor is there, moment resistance there, number of stories there, principal axis is there, then P delta effect, soft story, weak story. Okay, these are there. So this is the basic design, seismic design philosophy. So if you see the table, the ground shaking is divided into three categories. First is strong. So under this, based on the effect or the disasters which happened on the structure, they are categorized into three parts. The first is structural damage, then collapse of the structure, then non-structural damage. Okay, so if the ground shaking is there very strong, okay, very strong ground shaking is there, then the structural damage should be allowed, but collapse should not be allowed, but non-structural damage may also allow. So this is the safe, you can say, the seismic design philosophy of the earthquake engineering. If the ground shaking is somewhat moderate, in that case the structural damage somewhat low as compared to the strong one, then collapse is not allowed, then the non-structural damage is okay, not allowed. Then minor, if there will be a minor ground shaking, then structural damage is not allowed, collapse is not allowed, and non-structural damage. So I would like you to explain you about what are the various component of the building which are comes under the category of the structural part. So basically like beams, column, slab, okay, foundation, these are the parts of the structural. Okay, then non-structural are like a door, windows, okay, shutters, these are the non-structural damages part. Okay, so if you see in all the cases, Okay, then in that case nowhere the collapse will be allowed. So will be that will be your main and foremost important design philosophy, that in any of the case the structure should not be fully collapsed. This is the basic design philosophy of the seismic structure. Okay, so while designing or while analyzing the structure for earthquake, you must keep in mind these table and this philosophy. Okay, so next is design approach. So first of all, the structure possesses at least a maximum strength to withstand the minor earthquake, okay, which occurs frequently and without damage. The structure should resist the moderate earthquake without significant structural damage, through some non-structural damage may occur. And the structure should withstand the major earthquake without collapse. And finally, the actual force that appears on the structure during an earthquake are much higher than the design forces specified in the standard. However, the ductility arising from the inelastic material behavior and detailing and strength arising from the additional reserve strength in the structure over and above the design strength are relied upon the account for the difference in the actual and the design lateral loads. So this is the basic strategy of the earthquake resistant design. Okay, so H is the horizontal force which is acting. If you see the top diagram, okay, H is the horizontal lateral force which is acting on a frame. Because of that, the frame will try to twist or try to deform in rightward direction. So this delta, we have to take care of this in earthquake resistant design. So if you plot the graph between the delta versus the lateral force, okay, so first of all we will see the first horizontal line, that is a design force is there, okay, and second is the maximum elastic limit of the force there. So the maximum elastic force should be reduced by R is the response reduction factor which will be used, okay, which will be considered while analyzing the structure. So all the formulae and these R factor, H factor are available in your analytical part. We will see while we will solve the numerical parts. Okay, so adding to that, the structurally independent form and existing structure shall be designed and constructed in accordance with the seismic requirement for the new structure. And in addition to that also, the structurally independent from an existing structure shall be designed and constructed such that the entire structure conform the seismic force resisting requirement for a new structure, which follow the following condition. The addition shall comply with the requirement of new structure. The addition shall not be increased force in any structural element. Then the addition shall not be decreased in the seismic resistance of any structure element of the existing structures. So there are the assumptions based on that the earthquake design is based. So first of all, the earthquake causes the impulsive ground motions which are complex and irregular in character, changing in period and amplitude, each lasting for last duration. Earthquake is not likely to occur simultaneously with the wind or maximum flood or the maximum sea waves. The value of the elastic modulus of the materials wherever required may be taken as for the static analysis unless a more defined value is available for the use in such a condition. So these are the load combinations which are applicable for the earthquake resistant design. So if you see the load factor for plastic design of steel structure, if you go for the earthquake resistant design of steel structure, in that case the top three formulae will be applicable. Okay, and next one is a partial factor of safety for the limit state design of a reinforced concrete and pre-stressed concrete. 1.5 dead load plus live load. We have already seen the first part in IS 456-2000. Then second 1.2 times dead load live load plus minus earthquake load. Okay, so IL is the reduced load which is considered for the calculation of the mass. Okay, IL is the reduced live load which is considered for the calculation of the mass. So next is design horizontal earthquake load. So when the lateral load resisting resisting are oriented along the orthogonal horizontal direction, the structure shall be designed for the effect due to the full design earthquake load in one horizontal direction. So when the lateral load resisting elements are not oriented along the orthogonal horizontal direction, the structure shall be designed for the effect due to the full design earthquake load in one horizontal direction plus 30% of the design earthquake load in the other directions. So these are the some assumptions are there. Okay, so that is earthquake load shall be replaced by plus minus ELX. ELX means earthquake load is applied in X direction plus minus 0.3 times ELY. Y is in Y direction. Okay, and plus minus 0.3 times ELX plus minus ELY, whereas X and Y are the two orthogonal horizontal directions. So vertical ground motion. Let us see what are the effect of vertical ground motion. Earthquake generated vertical inertia force are to be considered in the design unless checked and proven by the specimen calculation to be not significant. The vertical acceleration should be considered in the structure with large span and those in which the stability is a major criteria for design and overall stability of the analysis of building. Then the reduction in the gravity force due to the vertical component of the ground motion can be particularly determinantial in case of a pre-stress horizontal member and of the cantilever member. So these are the combination of all the three components. Okay, if you consider both horizontal force in X direction, Y direction and Z direction, we will see all these calculations and basic part in our numericals. Okay, so let us move forward. Increase in permissible stress. Okay, increase in permissible stress in material. When the earthquake force are considered along with the other normal design, the permissible stresses in material is also increased in elastic method of design and may be increased by 1/3. Steel is having a definite yield stress, whereas the stress to be limited to be yield stress. For steel having without a definite yield point, the stress will be limited to 80% of the ultimate and the strain or 0.2% of the proof stress, whichever is smaller. Then soil structure interaction. So this is the another very interesting topic. Okay, we generally design the foundation for the fixed support. Okay, but soil structure interaction play a very vital role in designing the foundation as well as the structure. So the various criteria related to soil structure and their assumptions and their various tables and all that are available in IS 1893. We will see step by step. So the soil structure interaction refers to the effect of the supporting foundation medium on the motion of the structure, and it may not be considered in the seismic analysis for the structure supported on the rock or rock-like material. So these are the basic table by which the percentage of permissible stresses can be increased to allow the bearing pressures or the resistance of soil. This table is also available in IS 1893. These all are data are taken from IS 1893. You can refer that. Okay. Then the concept individual spread footing and in piles. Okay. So based on the different seismic zones, these are provided. Okay. Then important note in soil deposit consisting of submerged loose sand and soil falling under the classification. Okay, the with the standard penetration n value less than 15 in seismic zone number 3, 4, 5 and less than 10 in seismic zone number 2, the vibration caused by the earthquake may causes the liquefaction or excessive total or differential settlement. So these are the some parameters there. The next is the seismic zone map. This is the important part. This was also left in our unit number 1, so we can see that. So this map is there. Okay, so this is also available in your IS 1893 in the annexure part in the last pages. Okay, so based on the different color, the zone map of seismic zone map of India is divided. Okay, so if you see that the red colored patches, so the red color indicates the severe zone, that is zone number 5, and then based on that the zone are divided into major 4 zone. Okay, although there are 5 major zones, 1 2 3 4 5, but in IS 1893 2002 zone number 1 and 2 are merged, and these zone number 2 will represented as blue color in your map. Okay, so zone 2 is there, 3 is there, 4 is there, and 5 is there. Okay, so seismic activity in past earthquake. So these are the some of the data so of the earthquake which happened in India. Okay, so one of the major earthquake in the last 20 years was 2001 Bhuj earthquake. In that around 5 to 6 lakhs people were died in 2001 earthquake, and the intensity, if you see that, the magnitude was between 7 to 8. It was a very disastrous earthquake in the history of the Indian earthquake data. So seismic zone, town which falling at the boundary of the zone, demarcations line between the two zones shall be considered in higher zones. So these are the revisions. 1893 2001 code. The design horizontal seismic coefficient AH can be calculated as Z by 2 I by R SA by G. This is the calculation part. So in unit number 4, when we will analyze the building, okay, so this formula will be available or will be applicable, okay, for the calculations. So if you see the formula, AH is equal to Z by 2 I by R SA by G. Okay, R is the response reduction factor, SA by G is the maximum elastic acceleration, and SA by G is directly related to your soil structure interaction or your foundation data. Okay, then we provided that for any structure T should be less than 0.1 second, and the value of AH will not be less than Z by 2, whatever be the value of I by R. So these are the changes which are available in your IS 1893. Then seismic zone map, this is the factor value. Okay, for seismic zone number 2, Z value will be considered as 0.1, for 3.16, 0.4, for zone number 4 0.24, and for 5 0.36. So these all data are available in IS 1893. You can just refer that. Okay, so then step by step we will see all these. When we will go for the calculation. The next is your importance factor, 1.5 for your important buildings, and for other buildings like the factor is 1. Okay, so these are the changes in occupancy is available. Then lateral force R, the value of R can be taken from this table. Okay, then the next part is building system with both shear and brace frame. So this data will, or this part we will cover in our lecture. Okay, thank you.